Hello, so today I'm going to talk about some techniques for finding derivatives. Now, there are several rules that we have as it relates to finding or certain types of derivatives, for instance. The first one that I kind of want to start with is looking at the constant rule. So, what the constant rule says is that if we take the derivative of a constant, such as b, that's going to equal to 0. Now, the reason of which that it would equal to 0 is mostly because if you look at the graph of the constant, so like, we can assume y equals to b. Well, if you graph that equation, most likely you'll find that it looks like exactly like we would think. It's a horizontal line. So that horizontal line, essentially it's defined in the following way, where you have that it's y equals to b, but there is no slope. So if there is no slope, that means that, well, that technically the slope is equal to 0. Now, if the slope is equal to 0, then that must imply that the rate of change must also be equal to 0. Now, there is an easy way, though, to show, how do we know that the derivative of the constant equals to 0? Well, if for instance you were to say that you're taking the derivative of b, well, by definition, that's the limit as h approaches 0 of b minus b divided by h, but you can see that that just gives you 0. So what this tells us is that, yeah, that the derivative of a constant is 0. So if it's the derivative of, let's say, 1 or 2, then you automatically know that it's going to be 0. And then, of course, if it's like the derivative of pi, well, then that's just 0 too. Now, another rule that we do have as it relates to derivatives is what we call the identity. Now, whenever we talk about the identity, we're actually talking about the derivative of x. Now, I do have one way that I can show it using, for instance, like the graph, and how we just relate that the derivative is really just the rate of change, which is really just a slope, for instance. So if this was a slope or an equation of a line, then we would know that the average rate of change must be equal to 1 in that case, because if you think about y equals x, well, that's just a line. What's the slope? Well, it's just 1. So that means that the derivative has to be equal to 1. Okay, so the way of which that we can show this, though, is kind of like the same way how we use like the definition, for instance, which, I mean, that always is pretty handy, the 4 or 5 step rule. So we have the limit as h approaches 0 of x plus h minus x all divided by h, but you can see that, for instance, that the x's cancels out and you're just left with h over h, which must be equal to 1. So in that case, you just have that the derivative of x is just 1. Now, we also have a rule that we look at, for instance, like the squared function. So we have that we can call this the squared function. So traditionally, we'll just say that, okay, if we take the derivative of x squared, that it's going to be harder to look at the graph of x squared and then justify like what the derivative of that function is, or kind of like what's the slope, because now it's a little more complicated. But it's actually just 2x. Now, there is really just the way of looking at the formal definition that we can say that the derivative of it is really 2x. So what that means is that, if we go ahead and we kind of show it, like where we have the derivative of our function x squared is equal to the limit as h approaches 0 of x plus h squared minus x squared all divided by h. Now, this gives us that if we expand the parentheses, you get this trinomial x squared plus 2xh plus h squared minus x squared. Now, unfortunately, nothing really does simplify aside to the x squared is canceling out. So what that does is it gives us that it simplifies to the limit as h approaches 0. Now, because you have that it did cancel out, you have that there's a factor now. Yeah, let's just fix this. There's a factor of h that should cancel out. So that gives us the limit as h approaches 0 of, okay, so what do we have here? We have 2x plus h. But the only thing that depends on h is just the single h that's right there. So that gives us 2x. So that tells us that, yeah, the derivative of x squared is just 2x. Now, we do have another type of derivative, for instance. We have that there's the cubed function. Now, what that means is that the derivative that we're taking is of the function or expression x cubed. Now, this becomes more complicated as it relates to, how do we find the derivative of x cubed? Well, I suggest that you try showing, the derivative of x cubed using the official definition, formal definition, and just say that you'll find that it's 3x squared. Now, okay, so I'll just put that you should try to show that that is 3x squared. You can pause the video if you want. That way you can work out, how to find x cubed, and you're going to use the formal definition. Now, this leads me to the most important definition, though, or property, or whatever you want to call it, rules, which, yeah, formally we call it the power rule. Now, the power rule says that if you take the derivative of a variable x to an integer n, that's going to be equal to n times x to the n minus 1. But this is only valid for when n is an integer that's not equal to 0. Okay, so the thing of which that we can kind of look at, for example, is how we can say that if we want to find the derivative of x to the 9. Okay, so that means that if we're going to take the derivative of x to the 9, well, according to power rule, it says that we just need to pull the power to the front. So we have 9 times x to the 9 minus 1, which is just 9x to the 8. And then that's it. Okay. Now, there are a few more properties or rules that we need to go through from this section. Now, the next one is actually not too bad. It's called the constant multiple. Okay, well, the constant multiple is just basically taking the derivative of any constant multiplied by a function f of x, and then just saying that it's c f prime of x. Now for me, I can say easily that constants are just constants, so just ignore it and just factor it out. But of course, you can show it by saying if I have the limit as h approaches 0 of c times f of x plus h minus f of x times c, of course, divided by h, well, it kind of follows what I just mentioned, that constants are just constants, so factor it out. So we have c times the limit. That doesn't look too nice, so let's go ahead and clean that up. So we have that that's going to be the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Okay, now notice that in this case that the thing in the big bracket is really just the derivative. So that's c multiplied by f prime of x. So this is more or less like a little proof on, okay, the constant times a function is the constant times the derivative if you're taking the derivative. Now, in my opinion, this rule technically does tell me that I can find the derivative of, say, for example, a linear function, but I need more in order to show that. But let's go ahead and just look at an example of constant multiple rule. So, for example, let's say that you're taking the derivative of 1/3 x cubed. Now, 1/3 x cubed, I have that I'm actually using two rules technically. I'm using the constant multiple rule and I'm using the power rule. So I look at this and I say, well, the 1/3 is really just a constant, so if you want to remove it, you can, but note that, according to the rule, it says that as long as you kind of hold it constant, then it shouldn't matter. But we'll go ahead and just say, okay, we'll just take the derivative of x cubed then. But that's going to be 1/3 multiplied by, well, what is the derivative of x cubed? Well, accordingly, if you take the n and you pull it forward, you have 3x to the 3 minus 1. But what is that? That's 3 over 3 x squared. But that's really just x squared. Well, look at that. So you get x squared. Okay, so x squared is the derivative of 1/3 x cubed. Okay, now I mentioned that, yeah, maybe I can go ahead and take derivatives of linear functions or just create some kind of rule. Normally we do start with linear functions, but I feel that, yeah, you still need more before you move on to, like polynomials and things like that. So let's go ahead and work out another rule. So another rule basically says that it's called the sum and difference rule. So the sum and difference rule basically tells me, let's go ahead and just change that to sum and difference. Okay, so the sum and difference rule basically says that if I take the derivative of f of x plus or minus g of x, that this is going to equal to f prime of x plus or minus g prime of x. Now there is a way to prove this, but it requires that you have to take the derivative of the whole thing and then show that you end up with just the sum of those two. Okay, now in this sense that just means that, yeah, that if we take the derivative of either the combination, like the sum of it, then it's the same thing if you just take the derivative of each one individually. So what this is saying is that basically that, yeah, if we take the derivative of, say, like a polynomial. So like let's say like you have x to the n and then a sub n plus x to the n minus 1 and then an minus 1 plus a1x plus a0, where all of these an's are just constants. So what that would mean, and what you could do probably, is to say that all of that is equal to p of x. So if you were to basically just apply the derivative to every single term, well then that would give you equal to n x to the n minus 1, and then you would have an, and then you would have plus n minus 1 multiplied by x to the n minus 2, and then you have an minus 1, and then yeah, that's where you would get that this would be plus just a1. So what this is though, this is equal to, okay, in this case like you have that this would be equal to the derivative of p of x. So basically this tells you that you would be able to take derivatives of polynomials. So yeah, we have that this right here is a polynomial. Okay, so we have that that's going to be a polynomial. So you can see like how you have like, many terms being added, technically n plus 1 terms. And what that says is that, based on the sum difference rule, that tells us that, yes, that all polynomials do have a derivative. What are they? They're just the derivative of each term individually. And note that, that the derivative of a1x was by the constant multiple rule. Now in that case, that also tells me that the derivative of a linear function like mx plus b, that allows me to basically use a little bit of everything. So, if you want, you can label this as linear functions. So that means that, yeah, we can take the derivative of this, which by itself is just going to be m. But then if you see that if you take the derivative of b, that's just going to be 0. So what that means is that the derivative of a linear function is just the slope. But really, normally in class, like I would say, well, the rate of change that we know as rise over run, it's just basically the slope. So why, yeah, it's just the slope and that's it. Nothing else. We don't, I mean, that would be the most practical way to like kind of explain it. But in this case, we're using a little bit of calculus to figure out like, what that is. Okay, so let's look at an example of finding the derivative of a polynomial. So like let's say that we have 2x squared plus 5x plus 3. Now, using the rule, we have that that's just going to be the derivative of 2x squared plus the derivative of 5x plus 3. Now you can either change it as a linear function or not, it doesn't really matter. Okay, well that gives me 4x plus 5. It does give me 0, but I don't need to write it. So the derivative is just 4x plus 5. Now, let's see. We also have that we can take derivatives of any other types of equations, for instance. In this case, this was the derivative of a polynomial. So let's try to look at another example. Yeah, so let's try to look at another example, such as, okay, so in this example, I want to find the tangent line at x equals 1 when f of x is equal to the square root, so 2 times the square root of x plus x, and then we have that's going to be minus 1 over x. Okay, so what this does is it tells us that we basically just need to find the derivative of this function, and we need to also find what it is when it's 1. So what this tells us is that we have that, first off, f of 1 is equal to 2 times the square root of 1 plus 1 minus 1 over 1, which is actually just equal to 2. So that tells us that the ordered pair that it passes through is 1, 2. The next step that you need to use is that you need to find the derivative of f of x. So we take the derivative of f of x. So we have 2 times root x plus x minus 1 over x. Now there's a little kind of problems here. We have to say that the square root function has to be rewritten so that we can apply the power rule. So that's 2x to the 1/2 plus the x, but then you have to also rewrite x, 1 over x as x to the negative 1. That way we can apply the derivative, or the power rule. Now what this does is it tells us that we end up with the square root of x. So we end up with the square root of x, and then we have that that's going to be plus 1. And then we have that the second derivative, or the first derivative, sorry, will be plus x to the negative 2. Okay, so this gives me that I end up with the square root of x plus 1 plus 1 over x squared. Now, I need to find the derivative, or the slope of the tangent at that function for this function. So we have that f prime of 1, which is equal to the slope, is equal to square root of 1 plus 1 plus 1 over 1 squared. But as you can see, all of this is just equal to 3. So we have that the slope is equal to 3. Now, the question becomes, how do we find the tangent line? Well, you can either look at it as that you can use y equals mx plus b, or you can use y equals, or not y equals, but y minus f of a equals to f prime of a multiplied by x minus a, because that's the equation of the tangent line. I'm going to go ahead and just use the equation for a tangent line. So I'm going to use that y minus 2 equals to 3 times x minus 1, which is y equals to 3x, 3x minus 1. So the equation of the tangent line is 3x minus 1. Okay. Now, the other thing of which that, that we can try to look for example, is horizontal tangents. Now, horizontal tangents is basically whenever you have that a function has where the slope of the tangent line is equal to 0. So for instance, we have two of them. We have one right here, and we have another right here. But the question is, like, how do we find these points? There's a process to thinking about this. Like for instance, we know that this is y equals f of x. We know that y prime equals f prime of x is how to find the slopes of the tangents. So for instance, we know that the slope would be positive here, negative here, but at this point, that's where the slope is not anything. It's just constant, so it's just 0. So in this case, we have like f prime of x is equal to 0, and over here, f prime of x is equal to 0. But it's for a specific value, okay, so try not to get confused. Like, this could be 0, for instance, and this could be like negative 3 or something like that. So what you want to do is you want to find any equation where the slope might be equal to 0. So let's say that, we did consider an actual example of finding the horizontal tangent. Okay, so let's say that we want to find any horizontal tangents for f of x equals to negative x cubed over 3 plus x squared over 2 plus 6x. Okay, so this is actually not too bad because accordingly we just need to find where those horizontal tangents are for the derivative. So the derivative of this equation yeah, this is going to be equal to, okay, so we have negative 3 over 3x to the 2 plus 2 over 2 x squared, not x squared, but x, and then plus 6. Now, okay, so that means that the derivative of this equation is equal to negative x squared plus x plus 6. But let's just rewrite this again. So x squared minus x minus 6. Okay, so if we go ahead and we try to find where this function is equal to 0, so we can just say 0, then we can figure out like where those horizontal tangents are. So we have, if we just factor this, so we have that factors as x, and that's x, and then, well, 6 factors as 3 and 2, so we have 3 and then we have 2. The middle term is negative, so that means that this term is, or this factor is negative, and that one is positive. So what this means is that you have two horizontal tangents. You have one at where you say, okay, so this means that x minus 3, just do that, and do that again. So we have x minus 3, and then we have x plus 2 is equal to 0. So this means that x minus 3 is equal to 0, or x plus 2 is equal to 0, which means that you have x equals to 3, and you have x equals to negative 2. So the horizontal tangents are right here at x equals negative 2 and x equals to 3. Now normally you won't really be asked for the values of which that is, but if you do, you just have to figure out, like, for example, like what is 3 comma f of 3, and what is negative 2 comma f of negative 2. Now I have the graph pulled up on desmos.com, so if you go to desmos.com and you type in the equation, it actually graphs it for you. So notice that negative 2 was our value of which that you had, that was a horizontal tangent. Now that's like negative 7 1/3, and then if we click over here, that's 13.5. So we can actually go ahead and furthermore say that this one is 3 comma 13.5, and this one right here is -2 comma -7.333. Now, if you go back to the graph of the equation, this is where you had a horizontal tangent. But observing the graph, you can see that there's like a little saddle. So that means that this is a min, and then you have a peak right here, which means that that's a max. So essentially, that means that you have that it actually gives you more than what you think. Gives you both a max and a min for that equation. Of course, most calculators now can do this, where you just plug in the function and you just ask for the min and the max respectively. And then it can tell you also about behaviors of the function itself. Now, the last thing of which that I would like to talk about is about kind of like applications. So, for instance, we can actually look at, things like a cost function, which is usually given by C of x. We can also look at a revenue function, which is typically given by R of x. And then we can also look at what is called a profit function. Now, the profit function is actually just R of x minus the cost of x, which is equal to what we call P of x. So, for instance, because I just showed you that we can find the max and the min, then realistically you would want to minimize the cost, maximize the revenue, and also maximize the profit. But, if you look at the largest, let's say like the largest revenue, it might not guarantee the largest profit in that case. So you have to kind of be careful with that. Okay, but what I want to do is a little bit of what we call marginal analysis, where essentially we can actually figure out the cost of production for like the next item based on the derivative itself. So we'll just say that the marginal cost is basically taking the derivative of your cost function, and then that gives you C prime of x. So what that tells you is that the cost of the x plus 1 item is given by C prime of x. So if you're looking for the cost of the 22nd item, you'd be looking at the 21st on the derivative and then letting that show you. Now, there is a way to kind of figure that out, like if you were to graph that in the, well, like if you were to kind of consider like the x and y plane. So essentially you have that there's a function of which that you have maybe, I don't know, maybe it looks like that. Okay, so let's say that that's x, and then let's say that this is x plus 1. Okay, well then in that case you have that if you're going to use the definition, that means that you have the limit, let me see. So you're trying to find the cost of the x plus 1th item. So if you take the limit of, let's say, okay, so you're trying to find the x plus 1 item. So maybe it would be like this, where you have the cost of, let's say that this is x plus 1, and then you have minus the cost of x, and this is all divided by x plus 1 minus x, and you're taking the limit as x approaches x plus 1. So by definition, this is going to give you by definition, like when you figure out like that the x's both cancels out, this is going to give you that this is approximately, yeah, well, it is the derivative. Okay, so it is the derivative at x plus 1. I mean, in this case, we would probably have to uh, kind of look at it a little backwards, where you're looking at c prime of x, but it's supposed to give you like the same thing essentially. So this is kind of just notation. But anyways, we have that this is going to tell us that this represents kind of like the change, or kind of like just the cost of c prime of c of x plus 1. Okay, so yeah, because these two cancels out, and then it gives you the derivative. I think it should be backwards though, but we can fix it. I'll think about it a little later, but all I know is that, yeah, it's always given by the c prime of x. So what we can do here is look at, yeah, actually, let me see. Yeah, what we can do is just look at an example, for instance. So let's say that we have that the cost of production for a specific item is given by c of x, and this is 5x cubed minus 10x squared plus 75. So if I find the marginal cost for producing let's see, what is that? I think it's 100 items I wanted to ask. So yeah, so this is going to be for producing the 101 item. Okay, so we can also say 101 items. Okay, so what this means is that we just need to find, essentially this just means that you just want to find c prime of 100, because apparently that equals to c of 101. Okay, so this approximately is equal to c, well, c of 101. Yeah, this should be, yeah, I think it is actually supposed to phrase as like the 101 items. Okay. So what this is that it gives you that you find the derivative of this equation. So you have the derivative of 5x cubed minus 10x squared plus, I think that was supposed to be 75x. Let me go back. I have it saved. Oh, okay, that's correct. So we have plus 75 is equal to 15x squared minus 20x. Now that means that the cost, or the marginal cost, is 15x squared minus 20x. So what this does is it tells you to just plug in 100. So if you plug in 100, which you can by using a calculator, or you can say, well, I'd rather just you know, rewrite this expression so that way, you know, it's a lot easier, for instance. So I have 5x multiplied by 3x minus 4. And then from here, we'll just kind of figure out what is 100 plugged into this equation. So we have c prime of 100 is equal to um, is equal to 5 times 100, and then we have 3 times 100 minus 4. So in this case, like when we do this, this is going to be 500 multiplied by 300 minus 4, which is 296 or something. So then we can just subtract 4 from 300 and then multiply. So we said that it's 500 times 296, and then that's going to give us 148 $148,000. So that means that the production cost for producing 101 items is going to be $148,000 in increase. So that means that it's just going to be the increase amount. Okay, so what this means is that basically all that we needed to do was to look at the derivative when it came to the marginal cost. I feel like this should be, yeah, this should be minus c of 100, because technically you can figure out the cost of the 101st item by basically just taking the difference of the two. But calculus tells you that basically that all that you would need to do to find that change is to just use the derivative. Yeah, so I think that's why I was getting a little confused on the derivation back over here, because essentially this is telling me that like that the change in the cost, so like, you know, if I have that c of x plus 1 minus c of x, and I want to do that, that's actually the same thing if you just do the derivative of the cost function. Okay, alright, so this is gonna tell me, and yeah, I think this one, when we took the derivative of this, I think it was supposed to be just c of x, but I mean, it's just notation, to be honest. But the point is that you understand that this derivative is actually equal to the change in the cost functions, because apparently that's the algebraic way that you could do it, is just by taking the difference. So yeah, I would say go ahead and try looking at the actual cost of 101 items minus the cost of producing 100 items, and then see like what you get, because apparently this should be equal to approximately 148,000. Okay, if it's off by a little bit, that's okay, because I mean that's the nature of nonlinear functions anyways, because you'll find that the closer you are, the more accurate it will be, but the farther away that you are, the more inaccurate that it could be. And plus, it's just an estimate in the end. Okay, so that means that you will be able to figure out, like, for example, um, like what is the marginal revenue. So be sure that you look at you know, the marginal revenue, and also the marginal profit. But also look at, you know, finding like, for example, like you know, revenue and increased costs, or increased revenues and also, like, you know, profits and their increase. It would be interesting if you can look at when they are maximized, for instance. Okay, so that's gonna be it. do make sure that you look at the next section, which is over product rule and quotient rule and reciprocal rule.